Okay. I think we can get started. It's 3 minutes past 1, and colleagues can join us as they become available. Welcome to everyone who's joined us in person in Nico and online. Colleagues and students, you are very welcome to this research seminar, which will be delivered by our wonderful, I'm going to call you a new recruit, because relatively speaking, you're still a new recruit in the CSM department, our dear colleague, Dr. Nadine Abbas. This talk is titled Towards the Next Generation Communication Systems. I read the abstract and I'm really looking forward to learning about how you're going to bring together communication and computing resource management to solve some solutions around the heavy load that is being set on the networks nowadays. Really looking forward to it. I'm sure experts will enjoy it, and lay people like me will benefit greatly from your research. So when you're ready, Dr. Abbas, the floor is yours, and then we'll take some Q&A at the end.
Sure. Thank you for the introduction. It's my pleasure actually to be in your recruit and to belong to this amazing family. You know how much you're dear to me. So this presentation mainly will summarize the path that I took throughout the PhD and the research work, and how it was in a continuous evolution to reach now new trends also in communications. So hopefully it will be interesting to everyone, and it will not be, I will not go deep into technical details, so you will not get bored, so you'll get everything in the presentation. So if you allow me, I would like to share my slides. So can you see my screen?
Yes.
Perfect. So perfect. So this presentation is entitled Towards Next Generation Communication Systems. I'm going to start with motivation, the demands, the resources, and new trends of applications. And then I'm going to present towards solution resource management strategies in heterogeneous wireless communication systems. Then I'm going to focus on our work, which is joint computing and communication resource allocation in multi-layer device-to-device enabled heterogeneous mobile edge computing system. Then extended approaches and solution. And at the end, the future direction, conclusion and future directions. So as you know, we all use our mobile phones, and we're using the social media, we're streaming videos, we're watching Netflix videos, and we're overwhelming the system with a huge amount of data. What we use currently are the wireless interfaces, such as Wi-Fi, 4G, 3G, Bluetooth, and what we care about while using these wireless interfaces, the battery life of our mobile devices, the delay, we want to get the responses really fast, the best quality while watching the YouTube, for example, or any video. You don't want to see any freezing frames or loading, right? So you care about also about the price. So you don't use your 3G much, right? You try to directly go to Wi-Fi whenever it's available and stable. So these are the main challenges. We have scarce resources while we have tremendous demands. So back in 2020, they had a vision, which is the 5G life. It's the 5G flower, where they try to have a flower which will actually illustrate the needs, including user experience, connection density, where we cover a large number of devices. Approximately, they aim for 1 million connections per kilometer square, like in a very dense stadium, for example. They care about the mobility, the latency, energy, spectrum efficiency, and cost efficiency. So back then, this was the main target. It was like very simple and not advanced as we have right now, and not demanding as we have right now. So we started by proposing some approaches, user-centric approaches for real-time video streaming, while considering a balance between cost, energy efficiency, and we consider the quality of experience. So I'm going to show you a video. Definitely you don't want to watch this video with this quality, right? So what you want to see actually messy scoring. So for this reason, we provided solutions for real-time while providing the user real-time solution to provide the user with the best quality of experience. And we had several work published in this domain. We then moved to more dense networks, like we used the Camp Nou, similar to Camp Nou Stadium, where there are thousands of users. They are trying to download a common content data, such as video on demand streaming. So we proposed solution in order to like multi-user resource management in dense cooperative networks while meeting user service requirements. Also, we had several publications in this area. Then this is not enough. New trends of applications, they appeared lately, and some like Internet of Things, we have smart cities, intelligent applications, we have wearable technologies, we have virtual and augmented reality, remote healthcare, we do have the integration of artificial intelligence, industry automation, we have very critical and mission critical applications with very high reliability needed, Industry X.0 applications. We do have also the integration of drones in addition to cloud computing, edge computing, and big data. So actually by the recent statistics published by Ericsson Mobility Report last November 2022, the IoT connections are expected to reach 34.7 billion by 2028. We have computation-intensive, delay-sensitive applications, battery-powered devices, limited computation capabilities per mobile terminals, and we have definitely limited radio resources. So what we really need, intelligent real-time, energy and cost-efficient solutions, ultra-reliable and low-latency communications, in addition to ultra-flexible heterogeneous networks, where many nodes can cooperate in order to achieve the best performance in existing systems. For this reason, I'm going to focus in this presentation on the work that was published also recently, entitled Joint Computing, Communication, and Cost-Aware Task Offloading in Device-to-Device Enabled Heterogeneous Mobile Edge Computing, where we actually address joint computing and communication resource management in a comprehensive, multi-layer, device-to-device heterogeneous mobile edge computing, where we adopt partial computation offloading. That means the computation offloading is not directly offloading to one end only. It can be divided and assigned to several cooperating nodes. We have these cooperating nodes will be edge servers, cloud, and also we take advantage of peer mobile terminals which are available in order to provide the computational capabilities or services to other peer mobile terminals requesters. Definitely, we also adopt the communication, so wireless, heterogeneous wireless communication systems, where we adopt the use of the multiple wireless technologies in the same time, which currently exist. The goal is to maximize the number of completed computational tasks while minimizing energy consumption and minimizing the operational monetary cost. So we provided optimal solutions or optimized solutions, and then also we presented low complexity algorithm for large scale heterogeneous MEC networks in order to provide real-time solution in in microseconds, if you want, milliseconds or microseconds. So what we have as system model, if you can see here, we have the mobile terminal requesters, which are in red. You can see them here. And every mobile terminal requester has a computational task to perform. The task has a specific data size, a computation load or intensity, which is represented in cycles per bit, and it should be completed within a maximum delay tolerance. In terms of resources, we do have several cooperating nodes. So what we are doing is multi-layer, adopting multi-layer device-to-device enabled heterogeneous MEC network. What we mean by that is that we're going to use not only the cloud for MCC offloading, we're also going to use the edge servers and the device, the peer devices. And every cooperating node has its own computation capability. In terms of communication resources, since the cloud is not that close to the mobile terminal requester, we assume that the cloud offloading can be done through long-range wireless technologies such as LTE or 5G cellular networks. That means we're adopting mainly the orthogonal frequency division multiple access, where the bandwidth is divided into subchannels, and we can assign specific number of subchannels for a specific MTR in order to offload the data. For the edge servers, which are in closer proximity to the requester, we're using also the long range, such as Wi-Fi technology. We adopted the 5 gigahertz IEEE 802.11n, where we have a specific number of orthogonal channels, and we limited the number of orthogonal channels per mobile edge server or node. And we assigned one channel per requester, and we allowed the requester to connect to several edge servers in the same time. In terms of D2D offloading, so you can see here that a requester can send the data or the computation data to another peer mobile terminal using short-range connectivity, such as Bluetooth. For example, we adopted the Bluetooth Low Energy 5.0, operating at the 2.4 gigahertz with a channel of 2 megahertz. And definitely we have a limited number of orthogonal channels. One channel is assigned per requester, and we limited also the number of peer terminals or cooperating nodes helping the requester. Moving to the optimization problem formulation, the decision variables here mainly are we need to decide on the offloading decisions. So the amount of data that will be assigned or sent or offloaded to every single cooperating node and locally executed. We decided on the computation resource allocation by every cooperating node, and in addition to the communication resource allocation. For the multi-objective function, we are having a trade-off between maximizing the number of completed tasks while minimizing energy consumption and minimizing the operational monetary cost. For constraints, definitely we have limited computation constraints and communication constraints that I'm going to talk about in the next few slides. Starting with the decision variables, definitely we need to make sure that we have a decision variable, which is pi(i), that will indicate if a task can be completed or not. We need also to decide on the amount of data that will be locally executed or offloaded to the peer mobile terminal or to the edge server or to the cloud. We need also to decide on the computation resource allocation in terms of the fraction of computation resources assigned by every cooperating node. We're going also to decide on the communication resource allocation, including assigning channels for D2D offloading, assigning channels to MEC offloading, and assigning channels and the number of subchannels assigned for cloud or MCC offloading. For the multi-objective function, we have a trade-off between capacity, which is represented by the number of completed computational tasks within their deadline. We need to minimize the energy consumption while minimizing the operational monetary cost. We normalize the entity, the different objective functions in order to have a common scale ranging between 0 and 1. And we use the weights beta 1 and beta 2 as weights in order to indicate the impact of the different objectives. Starting with the first one, so it is in terms of pi(i), which is our decision variable indicating if the task was completed or not. For energy consumption, we considered mainly the energy consumed by the mobile terminals. So for local execution, for D2D offloading, which includes actually the communication, that means sending the data to the peer cooperating node MTJ, first the communication, then the communication also for receiving at the MTJ, and definitely the energy consumed by the cooperating node, which is in this case MTJ, in order to do the computation or execute the computational task. We have also the energy consumed for transmitting the data from the MTR, the requester, to the edge server, and also for MCC offloading. Moving now to the operational monetary cost, we're trying also to minimize the overall cost. We're considering the usage-based pricing model, which is in proportion actually to the resources, the use of resources. So we consider the computation price and the communication price. So in terms of computation price, we consider them as incentives for mobile devices, peer mobile terminals, to participate or to help in this computational or executing the computational task. And definitely we need to be subscribed with edge server and the cloud offloading in order to use the cloud and the edge servers. Definitely also, we're using the communication price, which is in USD per bit in order to transmit over the Bluetooth, Wi-Fi. Sometimes Bluetooth is free. However, here for general, in order to make our formulation general, we consider that we have charges even for Bluetooth. In terms of constraints, we have two sets of constraints. First one is computation constraints, where we make sure that the data size offloaded is less than the data size of the task, and no data is executed or offloaded if task is not completed. We don't want to lose or to waste our resources. The computation resources are allocated only if the task will be completed. The total computation resources are less than or equal to the computation capacity of every cooperating node. The computation resources are assigned only if data is offloaded to the cooperating node, and the task should be completed within its maximum delay tolerance, and the sum of data executed should be exactly equal to the data of the task in order to consider it also completed. In terms of communication constraints, we need to reserve a channel in order to do the offloading. So a channel is reserved to allow D2D, MEC, and MCC offloading when the task can be completed only, and when the resources are assigned and data is offloaded to a cooperating node. Then we have MTR can connect simultaneously to up to a specific number of mobile terminals, specific number of edge servers, and the total number of assigned channels are less than the number of available channels. And also the MTR is assigned a specific number of cellular subchannels once it's connecting or it's doing to the MCC offloading. We solve this problem, and however, this problem is a mixed integer nonlinear program, and it has a very high complexity. So it can be mapped to a general assignment problem, which is known to be NP-hard. So we try to linearize it. So we use several tricks in order to linearize it and get some solutions for specific or limited number of devices. Then we proposed a hierarchical allocation where we divided the problem into two subproblems. So we use problem decomposition in this case. So you can see that we have here, we solved the optimal problem, the problem that we already formulated, however, without considering the energy and the cost. Okay, so we solved the joint optimization of offloading decision, radio and resource allocation, while only maximizing the number of completed tasks. Once we have the solution, so we decide on the number of requesters which can be actually solved, then we solve this in order to do the allocation and provide the minimum energy and monetary cost. And by this, we're able actually to achieve results, optimize the results, but with less time complexity. Then also this is not enough. So what we try to do, and this is cannot be deployed in real-time scenarios. So this is why what we did is we provided solutions, iterative allocation, where we sort the mobile terminal requesters, and then we try to process one after the other and assign the resources one after the other. So for every MTR, we check the utility function, we check the utility function is mainly expressed in terms of energy consumption and cost. And we try to see if for every requester, if we are able to serve or actually to complete the task within its deadline, using all the available resources. If yes, then we can consider it for scheduling or resource allocation. Otherwise, we consider it as not served, and we do not waste our time considering or trying to process this requester. If it should be completed, then we try to check, can we do this, or can we complete this task locally without D2D offloading or without any offloading? If yes, then we are saving, or we're reserving the cloud, the edge, and the peer mobile terminal resources, and we go for local offload or local execution. Otherwise, we check, can we do it without the cloud? If yes, that's better to reserve the cloud, since the cloud can actually serve other additional users. So if we can complete it without the use of the cloud, then definitely we'll go for D2D and MEC offloading. If not, then we need to use the cloud. In this case, if we are able, you can see here, so if local execution, execute it locally. Else, we need to check if we need the cloud or not. So if we need the cloud, we're going to sub-problem 2. And if we don't need the cloud, if we need actually the cloud, so we're going to use all the resources of the available resources of the D2D and MEC, and then use the minimum, which is the on the cloud. And if I can do it without the cloud, what I need to do is check what is the best solution in order to offload. So just to show you some toy examples, and then I'm going to provide like more examples. So here in our results, in our results and analysis, what we did, we took a case study. So you can see here that we have 10 mobile terminals, and 4 out of them are requesters, and you can see them. These are in red. You can see them MTRs. Okay, we have 4 MEC here, the triangles, and we have 1 cloud. Okay. So we try to solve this, or we get the solution using the multi-objective optimization problem. And then we have the hierarchical approach, and the third column is the iterative approach. So you can see that all of them were providing the same solution. However, we have the execution time was 0.72 seconds whenever we're solving the multi-objective optimal allocation. And you can see here that we don't have any offloading because this task can be done locally. Since we have the data size is 1 megabit and the Tmax is 1 second. Now, if I want to move to a more strict or a stricter deadline, so here we're having 0.5 second. And you can see here that local execution cannot actually cannot be execute all the tasks. So what we need is actually offloading to the cooperating node. So you can see that the completed tasks are 4. So all the 4 tasks were completed, and we have a very similar solution between the optimal approach OA and the hierarchical approach and the iterative approach. Yet the execution time is very high for the optimal allocation. So it was achieved within 30 minutes. 12.45 seconds for the hierarchical approach, and the iterative approach 0.05 seconds. Now, larger data size, definitely we have more cooperating nodes should actually cooperate and give their resources. So we have the optimal approach was able to complete 4 tasks, hierarchical approach also 4 tasks. However, the iterative approach showed a suboptimal solution. Only 3 were actually executed. However, the time is very low. You can see here that the execution time is 106 minutes in order to achieve the solution using the optimal allocation, while we're having 81.4 minutes for hierarchical approach, while we're having like very execution time, very low execution time for the iterative approach. So here we extended our simulations in order to get a higher number of mobile terminals where we adopt or we considered 200 requesters, 200 device mobile terminals, peer mobile terminals, 4 edge servers, and the cloud. And you can see here, we actually compared our work with different work in the literature and state-of-the-art algorithm in the literature. And we were able to prove that our proposed approach outperforms all other approaches, even with high computation demands in terms of completed tasks, with a small trade-off in terms of cost trade-off cost in terms of energy and monetary cost. And if you would like to know more about this work, you can check our publication. We then try to, while we're doing our research, we noticed that if we're considering some tasks, and these tasks considered will be eventually dropped. So what we thought about is to have or to propose having an admission control before even trying to execute the task. So we can check if this task has a high potential to be executed, we admit it to the queue. Otherwise, there is no need to consider it. We directly drop it. So we don't actually waste our resources trying to process the task. So we proposed, another work also was published in IEEE Transactions on Network and Service Management. It's entitled SVM-based Task Admission Control and User-Centric Computation Offloading Using Lyapunov Optimization in Heterogeneous Mobile Edge Computing. We provided also optimized solutions and low complexity algorithm for real-time solutions. You can see here at every time slot, whenever we have a new task arrival, we check our model. So we build our model, SVM model, offline. And then whenever we have a task arrival, what we do is we check the current environment, the state of the queue. We check also the maximum data that can be offloaded to the different cooperating nodes, and we make a decision. Can we admit this task or not? And if we can admit the task, then we can assign the resources and put the task in the queue to be processed. And here are the results, also our proposed approach. Also, we compared it with different approaches from the literature, and we're able to prove that our proposed approach was able to outperform other approaches in terms of average queue size. So we're having stability. We're also energy consumption, percentage of completed tasks, in addition to monetary cost. This is not enough. We need more resources. So we need UAV-aided communication systems in order to serve ultra-reliable, low-latency applications. So in the first two work here, that we have a UAV-based relay system for IoT network with strict reliability and latency requirement, energy-efficient UAV-based relay system for IoT networks in hazardous industrial areas, where actually the UAVs are deployed in order to relay control messages in industrial hazardous area where we cannot actually deploy fixed base stations. So we use the UAVs in order to relay the control messages. And we also use the UAVs as FOC servers. So we proposed the minimum UAV FOC server with maximum IoT devices using genetic algorithms. And our recent publication, UAV-assisted multi-tier computing framework for IoT networks. And if you are interested to know more about the work, you can check the work. It is all the works are published. And reliability, energy consumption, and monetary cost. So what we need actually, or what we're focusing on, big data-driven, intelligent, wireless network design, operation, and optimization in order to use internet usage, data records, mobility pattern, user preferences, in order to provide This is it from my side. Thank you. Thank you. So